Hello everybody, thank you so much for coming. Welcome to this session. So this is session 3 of the ML study jams. My name is Vijay. You can see my picture here, very pixelated. But that's me somehow. I'm a tech lead at IIIT-Bangalore. I'm also a 4th year student here. I'm also part of a few clubs. But more relevant to the point, I'm also one of the teaching assistants of the machine learning course, which is currently running. So let me just introduce the session by saying that although this is a beginner-friendly series, this isn't the first video of the series, it's the third session. So if you see the first foray into machine learning, some things might be a little bit alien to you, especially some of the mathematics might be a little bit unfamiliar. But I hope at the end of the session you might get some nice idea about what classification is and how you can maybe pursue those fields a little bit more. So let's get started. So first of all, what is classification? So if you know, machine learning is basically getting insights from data, right? So over here, what insight you mean is, you have a set of data points, you have features, and you have labels. So labels basically tell you what type of feature it is. For example, let's say you had two images, right? Let's say you had an image of a person. This is a person, okay? Just imagine. Let's say also you had an image of like an animal. So now the task is, given any image, you should say which type of being is it closest to. Is it maybe a person or is it maybe an animal? Now the features of this could be anything. So if you know, images are basically vectors, right? So images are basically 2D arrays. So each of those 2D array or array is basically contiguous numbers. So for example, 2, 3, 4. This is an array. So if you can imagine each pixel being an array, you would have multiple pixels of the image, and this total set will form the feature. And there are two classes. One is, let's say, human, and one is animal. So the whole purpose of classification in this context is, given a whole data set of such data points, you have to find out the rules of determining whether something is a human or an animal, and you have to gauge with good accuracy or something with good metrics. Okay. So that is the essence of classification. Now we spoke about one use case, right? Humans versus animals. Now I want you to think about where this can be used. So please scan the QR code and type where you think classification can be used, or where have you seen it used in recent times. See, this is the same QR code. And if you type them, it will start showing up here. If you're not able to scan the QR code, go to slider.com and enter this code. Okay. Right, we have some things coming in. We have facial identification, which is very good. We have CAPTCHA. Now CAPTCHA, if you don't know, is that one thing that says select this spiral galaxy and all that. We also have handwriting recognition. This is really important. More than handwriting recognition, I would say, let's say given a set of characters, you want to tell which character it is. That could be used there. And so I think the point you begin to see is Google Lens, a nice program. You have a lot of use cases, right? Toxic comments, someone from the ML course here. And you also have future prediction. Now, future prediction is a little bit of an interesting thing. It's not necessarily classification, it's what's known as time series forecasting. But sure, if your forecasting can be divided into certain things, then sure, future prediction. So I think all of you can now appreciate the idea that classification is used pretty much everywhere, right? In a lot of places you have the expand setting and all that. A lot of places you have to divide your data into a certain class. And based on the class you have certain actions you want to perform, right? So it's almost like universal. So now there are a lot of algorithms, but with the help of some of you and some of these, we will discover a classifier from scratch, something that's actually used in the real world. So I would request a volunteer, maybe someone from the first bench. Anyone like a volunteer? Why also blank? It's okay. What's your name? Ricky. Yes, please come. So Ricky here is going to be the classifier. So what we'll do is so the task is, I'll give you the rabbit, and you have to hold it like show it to the camera like this, so that black side faces the key. Okay? And you have to go to the red side faces the key. Now Ricky, please stand in the center. Okay, let's say Ricky, you're standing here. Based on what you see, which color would you associate yourself the most to? Maybe I think it could be like distance. So why did you choose this person?
It's closest.
It's closest. Okay. So now let's say I'm standing here. and let's say I look at this, and let's say what's your name?
Siddesh.
Let's say Siddesh also is having what Ricky's having, sorry, what he's having. So the same color. Now what would you choose? Why?
It's more closer and say opposite, it's color.
You're looking at two things at once, right? So, okay, it is not this. So what Ricky has basically done is, he's invented the k-nearest neighbors classifiers. Please clap for it. So if it doesn't sound clear, let me give you a bit of intuition. So what Ricky looked at was the distance, and what Ricky looked at was nearest neighbors, nearest things to him, nearest people to him, and what color they were holding. And that is essentially what k-nearest neighbors does. So this is one of the simplest classifiers. What you do is, so features could be anything, right? I mean, we look at images being features, but features could have multiple columns, or let's say it was an Excel spreadsheet. Excel spreadsheets have multiple columns, right? So each column can be associated with a number. So that number basically forms a point in the coordinate plane. So let's say we have x, y, z, that's 3D space, right? Or x, y, we have a normal number plane which you might have seen. This is like x, y, right? So if you have two features, any point on that feature, or any point in that space could be something like this, right? So it has an x value and y value and so on. So for now, let's assume that there are only two features. So we'll have multiple points like this. Let's call it A, B, C, D, and so on. So what KNN does is, given K, so you tell, I want to look at the two closest points, okay? And let's say we're looking at two classes like we did red and black. Let's say red is 0, black is 1, okay? So let's say this is 0, this is 0, this is 1, and this is 1. Now, if I were to classify this point, first of all, can you all see this?
Yeah.
First, let's say I want to classify this point, and let's say I have to look at the two closest samples. So what class would it be, 0 or 1? How many do you think it will be 0? Please raise your hand. There is no right or wrong answer, to be honest. And how many do you think it will be 1? And how many of you will be guessing? Okay. It will be 0, right? Because A and B are the two closest points to E, and they both have 0. Now let's say this was 0 and this was 1, and let's say E was somewhere here. Now what would you assign the class for E to be? 1, right? Now that is basically what KNN does. You look at the nearest points and you take the majority or whatever classes they have. So let's say it was 3 points and it was 0, 1, 1. You would assign 1. So what Ricky has done with the help of the volunteers is basically quote unquote reinvented KNN. Now KNN is actually used in many places. So let's say the data is in such a way that it can be assigned to different clusters. What I mean is, let's say one part of the plane is one class, one part of the plane is other class, and we have such a decisive boundary. Then actually, if you put it like that, whatever k you give, it will belong to that boundary only. No, if you don't have points just spread out, then KNN will be helpful. But KNN is not always the best. There are some other classifiers as well, and we'll look at one more K. So I know what you're thinking. Can we extend linear regression to classification? You're probably not thinking about this, but I think about it now because I've just written it here. So if any of you have come to sessions 1 or 2, we spoke about linear regression in detail. And if you don't know what linear regression is, no problem. I'll come to that now. But so okay, for now you can assume linear regression to be given a point x is equal to, let's say, some feature space. So let's say you have n features. You give some y that belongs to R. Okay. So this is the function. It takes a point in n dimensions, or let's say 2 dimensions, and gives 1 point out. So for all the points in the space, you can assume that you will get a vector of like 1. So for example, if you have 5 points, you will get a vector will have something like 1, 2.5, whatever it is. Okay. Now assume that all of these points also have a label. Let's say this label is 1, this label is 1, this label is 0, this label is 1, this label is 0. Or let's say this label is also 0. So all of the points, the 2D points, have a label associated with it, and somehow magically you have a function that will take that point and it will give you a number. Now the question is, given this function, can you build a classifier out of it? Can you say that given this number line, given all the points here, can I tell another function that will tell you, given that you give me the value of y, I'll tell you if it's either 0 or 1. Can anybody please think of anything? Anything that comes into your mind? So you are given a function that will give you a real number. Now based on that real number, you have to choose whether it's class 0 or class 1. Any ideas? Maybe to concretize this, I'll put it into code. Before that, The way y is constructed is like this, okay? So basically what you do is, given all of the points in the data set, you plot those points onto a kind of graph and you draw the line. So this red line is basically a function. You're trying to estimate these points at this line, okay? And how that is, if you remember the mathematics behind it, we had a target variable which is which is the y. Give me a second, please. Yeah, we had a target variable which is y, and we represent it as a linear sum. So line is a linear sum, right? So you put like, what is line ax plus b? So a and b is what you would learn basically, the features. Sorry, the weights, and x is the feature. Let's assume. So you basically learn a line, and the learning means that you find out the best values for a and b. So if you represent y as a and b, you need best values, right? And how do you find out the best values? By computing it through a loss function. And based on a loss function, so loss function basically tells you how bad your current parameters are, and you want to make it get better, right? So based on how bad it is, you choose the next best parameters to put. That's called gradient descent actually. So maybe as a bit of a refresher, let's say I have a function x squared. You want to find the minimal of the function. How do you do it? So this is for everybody. Let's say have any function. You want to find the minima or the maxima. How would you do it? Correct. So with a vector function, differential is called gradient. Okay, I might have seen it. And so gradient descent basically, instead of equating it to 0, you go in the opposite direction of the gradient. You keep going down. That way you get it. So if the gradient is, so the function is like this, let's say. The gradient is here. Now what will be the slope direction, up or down? Okay, let's make it easier one. That's very controversial. Let's say here, this is a function. How would you, what will the direction of the gradient be? So would it be like this or would it be like this? Second. Okay. So basically what you do is, you follow the gradient down and eventually you will come to this point. This is the minimal. Okay, this whole thing is called gradient descent, okay? And that is what you do to basically find out a and b for linear regression. Fine, now that all of you have a general idea, any doubts about linear regression, whatever was done, you know? Okay, so this is the loss function. So loss function basically for all the points like this, let's say you estimate a line like this, you take all these distances and you square them and you add them up. Okay, that is the loss function. So you can think, right? If the line is let's say your points are like these 3 points. Let's say a line is here versus your line is here. Which one will have lesser loss function, A or B? A, right? Because they are somewhat closer. The distances are minimized. The idea of linear regression is you find the best line which gives you the least value loss function. Okay? So that gradient, like I said, is defined by this matrix format. Don't worry, this doesn't make sense now. You can always refer to our previous videos. It's all recorded there, as you can see. Next. So let me reiterate the question. Now that you know what linear regression is, you fit a line to data, and that line, if you give a point, you can plug it into the line basically, and it will give you a real value. No? So how do you classify that real entry into 2 classes? So to concretize this, let's say I have a function like this. This will compute the output of the line, and you check for a condition. If that condition is true, you return 0 class or return 1 class. Now what would you fill in this? Any idea? So by above the line, what do you mean?
Value of y for that x, value of y content of the point would be more than what we get when we plug that x.
Okay, that is one way. Any other ways? That's an interesting. Any other ways?
If you calculate the net input and we can find if y input is greater than 1 or y input is less than 1, we can know the accurate one.
Correct. Yeah. That's a nice suggestion. So what he's trying to say is basically, you take this y and you see if y is greater than or equal to some number, and if it is, you assign 1 class. If it's not, you assign some other class. That's what you said, right? So that's typically done. So in this case, I put y less than or equal to n. It's the same. If it's greater than or equal to, you assign the reverse class. So this is one way, right? If this doesn't make any sense, see, you have a function. That function gives you a number. You want to split the number line. You want to basically split the number line into 2 classes. So if you have a number line, these are all the possible values, right, which you can get. It's a real number. So what you do is you put something here. If any value is less than this, is 0. If any value is greater than this, is 1. Okay, that makes sense. But now the issue comes is, what is that value and how do you find it out? That is why this classification part comes in. Now, technically, with that loss function and with the gradient, You can build a classifier. It is definitely possible. But since your outputs are only 0 and 1, you can assume how small your loss is going to get. Because see, what is 0.1 minus 0.2? Minus 0.2. What do you do if you square that? It becomes very less, right? So if you think, yeah, 0.01 exactly. So if you keep on doing this, your loss function might become in such a way that you get arithmetic errors. So you get, when you try to do something in Python, you can't compute over some big number. And at the same time, when you go to very tiny numbers, you start getting error. In fact, I would encourage you to try. So open up Python or any programming language. You try finding out what is 0.1 plus 0.2. Let's see what you get. In fact, I also tried here in case you want to Python installed. So I'll go to Python. So obviously, what would you expect here? You expect 0.3, right? But what you get is not 0.3. So the reason for this is you'll get it on the DD class eventually. But there are some floating point issues, and these issues get aggregated with smaller quantities. Okay, so that's why we typically enhance this kind of linear regression to make it fit the classification problems better, and that is called logistic regression. But before that, before I motivate logistic regression, I want you to answer a few questions based on what you've learned right now, what you've understood. So again, please scan this QR code, and now you should see the second question. This is the second question. So the question is, our current loss, which is finding out the distance and squaring it and adding them up, is for linear regression. Do you think we can make this thing for logistic regression based on what we just discussed? I'll give you, already you can vote, right? You can see the question, right? Okay, I'll give you a few seconds to vote, please. I like whoever answered not sure. Nice. So, it will be explained now, okay? Okay, cool. I guess you can freeze voting. Majority of you say not sure, some of you say no, some of you say yes. The answer is no, but I'll explain why. Okay? And if it's not sure, I really appreciate it. Thank you for being honest. Next. So now we have, before you answer, now we have the threshold, right? So what we want to do is between any real number minus infinity to plus infinity, we're drawing some kind of line saying left is 0, right is 1. Now let's say we want to restrict this domain to 0, 1, and we have to draw some other line here. Which one do you think is easier according to you? Do you think for the whole space drawing a line, or for some smaller space drawing a line? Which one do you think is easier? Sorry? Yeah, answer. That's a question. So this if small space drawing a line is easier, then answer is no. Okay, we are getting lots of answers. A lot of you say yes, some of you say no. It's almost equal now. So intuitively only think, right? Let's say you had 100 balls to pick your favorite one, or let's say you have 2 balls to pick your favorite one. Which one is easier? Or let's say if you're going out to shop and you have a very indecisive friend, which one it would be easier? If you go to a big mall, or if you go to a small shop? So 0 to 1 is intuitively easier, but why? But one more fact you might ask is, doesn't 0 to 1 also have infinite numbers between them? That is correct. But the way logical regression works is, by suppressing the domain to a smaller number, you can find anything faster. And here's how. So logistic regression is a classifier that builds on top of linear regression, and it helps to solve this by changing the loss function and a few other things. But now you might be thinking, why is logistic regression called a classifier? And there are 2 separate things. And it's a good question. Let's see why. See, first of all, let's look at the questions again. Like all of you have mentioned, smaller range is probably better, and bigger range also might have like adding issues and squaring issues. Okay. So what you do in logistic regression is you learn. So what you do in logistic regression basically is, what you have now, you have a matrix X which has all the features, right? And you have a matrix Y which in this case we'll assume has 0 or 1. So if you have, let's say, 100 data points, you'll have, this will be a vector of 100 length, and this will be like features. Okay. So what you do in logistic regression is, again you learn a line only. You learn some kind of line. So let's say W0 X0 plus whatever. You learn a line and you learn these W0s. Now what you do is, given that line, given y gives you something from minus infinity to infinity, you basically create a new y hat which lies between 0 to 1. And now based on this y hat, you draw the line in the middle. Say if it's above 0.5, it's class 1. If it's less than 0.5, it's class 0. Now this 0.5 is normally done arbitrarily, but we can see if you have to change it or not. Okay. So this is the new loss function. Again, this might seem very counterintuitive, but the idea is instead of taking mean square loss, you get a much bigger variation by taking log. Now what is log any base 0.5? Is it positive or negative? Negative, right? So but loss function should be positive, right? So that's why this is minus n here. So what you do basically is if your if your prediction is 1, you take the log of that, and your prediction is 0, you take a separate log, you add them together. So this is called log loss. Okay. If this isn't very intuitive to you, or if you don't understand it, no problem. I have put a resource on the description for you to see. But the purpose of today's class, along with introducing the mathematical notation, is showing you how to make a very robust classifier. So right now, assume that lossy regression has something called log loss, which gives you a positive number at the end. And this is a function which converts minus infinity to infinity to 0 to 1, and that's called the sigmoid function. So what it takes is it takes the exponential of minus x. So 1 by 1 plus e plus minus x. So e power x, all we know what e is, right? So e power x, does it give you positive value or negative value?
Positive.
Does it always give you a positive value? So will this always be less than 1? And e power x will never give a negative value. So will this always be greater than 0? So do you see why the range is coming? Any doubts? Anybody? Okay. So let's recap, right? That's a lot of maths, I understand. So let's recap. What do we learn? So basically, we learn a line. We fit all the points of the line, and then we use the sigmoid function, that e power x function, and we make it into 0 to 1. After doing that, we calculate the log loss, and based on that, very similar to what we did in linear regression, gradient descent, that going down the graph, we do that here also, but the values are calculated using the log losses. Okay, now we do that, and at the end, what we'll get is, we'll get a line by which, if we fit the line, then do sigmoid, you will have a very good chance that if you predict above 0.5, it's actually class 1, and below 0.5, it's class 0. Okay, that's the essence of logistic regression. Is it clear? Any doubts? The people who answered not sure, is whatever you are not sure about, is that clear now? Okay, please raise your hand up if it's clear. Or not? Okay. Am I speaking too fast? Yeah, okay, thanks. Should have asked. Okay, I'll speak to it. Okay, just to recap, linear regression is you have all these points and you fit a line through that. Correct? Logistic regression, again you fit a line. But after you fit the line, because it's from 0 to 1, this range will come through sigmoid. Okay, and now sigmoid is this line. No? So at 0.5, what will it be here? No, middle. So you threshold it here. If it's less than 0.5, all of these points, so till here, these are all class 0, and all of these points are class 1. Okay, is this clear? This was clear? Okay. Now, if you are a little bit confused about logistic regression, a little bit of the mathematics is confused, don't worry. From now on, you won't be looking at this. Okay. But before that, let's try actually putting on into practice. So please scan this QR code, and you will go to Google Colab. You have to click on make a copy. Okay. This is on your computer, by the way. So just scan the QR code maybe, and you have to go to your computer. So you can take a picture and maybe copy the link to your computer somehow. So the only thing you need to learn, the only thing you need to know before you open this is, like linear regression, you learn a line, but you make that line smaller. You make the output smaller, and based on that smaller output, you guess which class it is. Okay? With that in mind, now I encourage you to open this. I'll also open it now. Okay, now you would see, since this is my account where this was made, you have to make a copy, which you can do via file, make a copy. Okay? Now, if any of you have seen this for the first time, let me increase the font size a little bit. Can you all see this? Okay. So this is basically a place where you can run Python code like on your browser. Okay. Now a lot of the syntax may be new. I'll just tell you what this is. So this whole part you can leave. What we're doing is we're loading in data. So I said no, X will be features, Y will be labels. So that data we are loading. Okay. So now you can see what it looks like. So basically that give me a second. This will take some time. Yeah, it's a shift plus enter in case you want to run it in this cell. So what we're doing is, so this data will look something like this. Okay, it has 4 features. You can see this is 5.1, 4.9, and also let me turn off the lights. Okay, all of you can see this, right? So what we're seeing is we have features that look like this. We have 5.1, 3.5, 1.4, 0.2. So these are 4 features that belong to this data point. Okay, data point 0. Like that, we have many data points, and why we have is like this. So why the first 5 data points all have class 0, but there are other classes also. We have class 1s and class 2s. And how many of each? We have 50 of each. So what do we have? We have 150 data points totally, right? 50 plus 50 plus 50, out of which we have 4 features for each data points and 1 label. So what we want to do is basically create a model that will somewhat classify this. Now before that, what I am doing is I am taking this 150 data points and I am removing 50 from them. I am taking only 100 and building a classifier and testing it on 50. Why is that important? Coming soon. But broadly that's generally done. Okay, you split your data into train and test, and you use a training data. Fine. So we can see that. So training data has 100 samples and 4 features, and testing data has 100 sample and 1 label, 0, 1, 2. Okay. Now this is logistic regression. So I am importing this from sklearn. So sklearn is one of the libraries. So library is basically a bunch of code written by someone else, which you can then load into your code. So instead of you writing all this and hence doing your manual process, and you can load it up from somewhere and you can run it. So I am loading up their logistic regression, what we just saw. Okay. So I am loading them up and I am calling it. So that variable is CLF. So this CLF is now my classifier. Now you might be thinking, what is all this random state, max, iter, TOL, all that? So the way functions work is, this is a function. Okay, you call parameters. So these are your parameters, and what there you can see in comments. But just assume that I am running that gradient descent step for 5 times maximum. Okay. So what I mean by gradient descent step is, whatever parameters you have, you compute the loss and change the parameters. No, that I'm doing 5 times. Okay, over here. So I made a classifier and I built it on the data, and I get a 68% score. Just one less than nice. Anyway, let's say now I increase this to 10. Do you think the accuracy should improve or become worse? Worse. Improve. How many do you think it should improve? And how many do you think it should be worse? Okay. And how many are not sure? Thank you. So, to those of you who said it should improve, why? Anybody like to volunteer? Was it just divine interventions? No, see, the idea is you are computing the loss and you are changing the parameters. Now, if you do it more times, the idea is it should become better, because every time you are becoming better than the last step. So, if you do more steps, ideally it should become better. Now, sometimes this will not work, but in this case, let's see what happens when not. Okay, we get 100% accuracy. Now, some of you may be very delighted, and there's a good reason to be delighted. 1.0 or 100% accuracy is good. But let's say this max item, let's keep it at 3 again, and we change some other parameters. Now we might get a different result again. Sure. But what I wanted to see is basically each module has different parameters, which you then change and you tweak around, and you see what's best for your use case. Okay. So I hope you found this demo interesting. But you got the idea about your number of epochs, right? This one, max item. Right, let's go back to the presentation. Okay, so we learned about 2 classifiers. We learned about k nearest members, and we learned about logistic regression. But what's next? Can I keep on going over different classifiers? I can, but I don't want to, because I didn't make slides. So from now on, You consider a classifier to be a black box. Basically, it's a magic thing. Okay, I give it some data, it will give me output. Let's leave it at that. Okay, that's it. So if at all nothing is clear to you now, you just now you can make out. Okay. So everything from now should become clear, and I'll turn on the lights for the recording again. Right. So like I said, from now on your classifier is a black box. You can assume that it will give you some kind of results, and now we'll see how to build a good classifier. Not via modules, not via Python, but generally. Okay? So the first thing is right now we looked at two classes, so 0 or 1. But in theory, and we just saw as well, there were three classes, no? That the 150 data points. So how would you handle multiple classes? So there are two methods. Let me explain them. Actually, there are more than two methods, but this is an introductory class, and I don't know about the third one. So the idea is, what you can do is, so right now we have two classes. No? Given a data point, we can tell either if it's 0 or 1. So let's say we have three classes. Okay, let's say we had A, B, or C. What you can do is you can build three classifiers. One to tell if it's A or not. So A or not. One more B or not. And one more C or not. Now, given a data point, let's say your classifier output is A is 1, B is 0, C is 0. So which class would this belong to now? A, right? Similarly, let's say if it's 0, 1, 0. B. Now let's say it's 1, 1, 0. Now what do you do? Good question.
Both.
It can't, right? Because by definition of your problem, your output point can only belong to one class. So if you have that restriction, what will you put it as? It's a good question. Which is sorry. So okay.
Which classifier is more accurate?
That's a good way of doing it. So what he's saying is, let's say we fit it on three different data sets, and A is the best classifier. It has 98% accuracy. So I trust A more. That is one way of putting it. One more way is, many of these classifiers come back with probabilities. I am 82% sure it's A, I am only 18% sure it's not A. So if this one is 82% sure, this one says let's say 50% sure or 52% sure, you trust A more, right? So this whole method is called one versus many. Okay, does that make sense why it's called one versus many? Because for each classifier, you are predicting if it's part of the one class or any other class. And you make many other classifiers. These scientists would have laziness. So next, like I said, some classifiers themselves have support for multiple classes. So like it's just a logic regression. We saw the what's called bivariate class. It has two classes, 0, 1. But the demo we did, it has three classes, right? So some classifiers actually can give you outputs that will tell you which class it is from 1 to n at once. So the way they do it is typically with more complex loss functions and prediction functions. But behind the scenes, they can also do something like one versus many. So typically, the best idea for us to implement is this. You take a classifier, it will do the job for you because we are lazy, right? So in case you are interested about how logistic regression can support multiple classes, just look into multinomial log loss and it will be good. I have put some resources in the end for you to see. So this part is clear to everybody? Any doubts? Anything? Okay. Now, what we saw is we had three classes, right? We had A, B, C, and we had 50, 50, 50. 50 examples of each, right? So it was somewhat balanced. Let's say we had 10 for 6 examples of one class A, and let's say we had 36 examples of B. Now, does this seem like a very realistic scenario? Do you think this can happen? Mr. Bharat is here, this project has this. So, this is definitely a very realistic scenario. Let me give you an example, okay? Let's say looking at credit card fraud. Now, luckily, humans are such that they do not produce fraud so much. So, if you look at all the transactions, a lot of it is actually not fraud. But you have very few examples that is actually fraud. So, in such case can happen. Now, of course, 10 power 6 and 36 is quite an extreme example. But let's say you had 70-30 split. Could happen. Let's say you had 60-40 split. Could also happen. A lot of things can happen. But now, as an ML engineer, your job is to decide what are you going to do with this. Because the baseline model or the rule of thumb is whatever classifier you build, it should be able to beat random selection. So if you give some random person on the anywhere, you say bro pick something, they'll say class A, you should perform better than that, right? But if you had a 90-30 split, let's say 70-30 split, at random, if you predict everything to be 70, you have 70% accuracy there only, no? So you have to do something better than that. Now, so the major method people do is, they make the data and they change it into some way that looks somewhat balanced, that looks like 50-50-50. So let's say I have, let me use the props again. Let's say I have 2 rackets facing black to the camera and 1 facing red. I have to make a new data set out of this to make it equal, 1-1. What do you do? What can you do? We can throw one racket out. So you take the majority, remove some examples so it becomes even, right? Or I take another racket, I buy some other racket from somewhere and I have two things. Two things, right? That's what these 2 points are. So if you take the majority class, you do what's known as undersampling, which means getting rid of some points. Or sampling is basically like, you have probability problems. So you select 10 balls from a box, that's called a sample. Okay, now some of you may get PTSD from your school days. But that's called a sample. So basically you're undersampling a particular class. So you're removing a rearray. Otherwise, you get some new data or you generate some new data for your smaller classes or minority classes. That way you will have 70-70. That's called oversampling. Now there are many techniques for oversampling and it is a little risky operation, but I would like you to introduce one method which I'm sure you might find interesting. And it's very intuitive. Now if you are to try to be certain the term it's intuitive will be seen very soon. It's a very famous algebra teacher. So let's say you have minority class like this. Okay, let's say you have 3 points A, and let's say you have multiple points B, B, B. So obviously, let's say you have 100 points here, let's say 30 points here. So which one is the minority class here? A. So if you want to do smooth, you have to add A, right? So the way smooth works is, it takes 1 point here, and like draws a line between them, and it starts cutting them into different points at evenly spaced points, and it makes a new and makes this point there, this point there, this point there, this point there. And otherwise, let's say you have 2 points x and y. You take like this. You take let's say x plus 0.1 into y minus x. So what is this now? 0.1 y plus 0.9 x, right? So what is this now? It will be like x plus 0.1 of this distance, which means somewhere close to x only, but on the line between x and y. And now what it does, it computes a point like this and assigns this as a new point. It adds this point. So that's what smooth does. So it's called synthetic minority oversampling. So it's a very interesting technique. But do you see why it makes sense though? Because if I have 2 points, you'd expect that all the points between that also belong to the same sample, right? So that's why it makes sense. Maybe is it clear for everybody? Any doubts? Yeah.
So small is just like adding the new classes.
Correct.
Between x and y.
Right. So your point about adding new points is correct. But see, what is a class? Class is A or B. So you're basically adding new points of class A. Does that answer your question? Okay. So what his doubt was, does smart add new classes? So to maybe reiterate, classes is like labels. Classes is a human or dog. Points are the actual humans. Points are the actual images. So smart adds extra points or extra images of humans. So by looking at all the humans in the space, it takes an intermediate human and it adds that to the set of humans. So let's say if dogs are more initially, you would have now equal amount of humans and dogs. Okay, so your doubt was, does it add more classes? Which means, does it add something more than human dog? No. It just adds more humans. Okay, does that answer your question? Okay. And one more method is the more practical method also. Some models allow you to specify which class is more, which class is less. And based on the fraction, it will update its loss function. So for example, if you misclassify a small a point of the minority class, it will give you higher loss. So there are certain loss functions that do that also. Okay, that's typically the class weights parameter. You can always check out the documentation what is there and you can work on it. Okay, but if you were to build a classifier, you have to look at more than one class, how you manage, and if your data has class imbalance. So if your data has imbalance, 70-30 split, how will you manage that? So you either add more points or you remove points of the higher class, or you will pass class points. Okay? Is this clear? Okay. Clear, bro? It is a big thing if you think about it. Okay. Next, how do you test a prediction? So like I said, we split it into training set, testing set. 100 we put to train, 50 for testing. How do you test it? So what is the most natural way of testing your classifier? Any ideas?
Setting it up in random environment.
Okay, no, like in practice. So let's say I have a classifier that will tell you if it's red or blue. So I'll give me a DT racket. I'll tell you if it's red or blue, or sorry, red or black. Now, how would you test what I'm doing? You
If you know the label already,
sorry.
if you already know the label, and we will input that sample.
Correct, exactly.
Learning it from the previous experience.
Yeah, paper. So I would learn from previous experience. So I would learn it from, if I'm the classifier, I would learn from other PT batch what color is it. But now you have to tell me, so now you have to test me. So how would you test? So you would have, you will ask someone to bring 3 TT rackets over. You will get some new data. You will ask someone to bring 3 TT rackets over. Then without showing me, you will compute what it is, red or black. Then you just show me the bat, and I will tell you red or I will tell you black. So now what is, now given that is the case, what is the most intuitive way to tell you or to tell me how good I am? Like accuracy, no? If I have predicted 10 bats, I have said 7 of them are red and 3 of them are black. And out of those 10 predictions I made, 8 of them are correct, 2 of them are wrong. So what will the accuracy be?
80%.
Right. So accuracy is one metric, right? Do you see how it can be useful? We used accuracy last time, no? The demo. We had 68%, 100%, 70%. That is accuracy. But do you think accuracy will fit all situations? Is the question. Does anyone think it's yes? Please raise your answer. If no, please raise your hand up. If you're not sure, please raise your hand up. Nice. So the answer to it is no. So like I said, again the same scenario. If I have 1,20,000 rows and 200, let's say I have 1,20,000 transactions, okay, and I have 200 features, a very big matrix, okay. You can imagine how big it is. 200 into 1 lakh is what? Rolls Royce. And again, I had binary classification: 0 for no fraud and 1 for fraud. Okay. So let's say someone has gone to a competition and they went, okay, I will submit something. My first attempt, I'll just see how it goes. He made, let's say they made a model which trained under 2 minutes. Now, if any of you have studied ML before, working with data as large as what 2 GB is quite a big task. And normally a model is not trained within 2 minutes. It takes a few hours. But this person's model 2 minutes, bro, crazy. It had more than 95% accuracy. So, and now when I asked them, show me your code, they sent me this. What do you think? They asked me to guess. So naturally I said, I'm keeping the talk, I'll ask them only. So let me ask you, what do you think they wrote in this blog? So just to recap, 0 is not fraud, 1 is fraud. So this person wrote a crazy model which had only one line and which gave 95% accuracy somehow. Correct. It just returned 0 into that whole array. It gave 0, 0, 0 everywhere and it got 95% thing. Accuracy is sometimes not enough when you have imbalanced data. Because you should do better than random choice. And if your random choice only is not random, what is the point? Which is what you want. So, like I said, again, accuracy is not enough. You have to account for class frequencies, right? One good way is the F1 score. So basically, it takes care of false positive and false negative. Now, what is false positive? Let's say someone mailed you saying tomorrow no class is there. That's a false positive. There's actually class. Similarly, reverse. If someone said class is there but it's not there, that's a false negative. Okay. By class, I don't mean this class. I mean your actual class. Yeah. Now, while training, we saw it, number of epochs, we saw other parameters. There are two things that can happen when you train the model. One thing is, the model doesn't train only. So let's say you updated your parameters have not updated well enough to fit the training data itself, to fit whatever data you given itself. So a good analogy of that is, let's say you're looking at, so this overfitting, underfitting is for any kind of model. So since linear regression was the most intuitive here, let's say these are the points for linear regression. Again, regression means you have to learn a line, okay? Let's say you put your line at something like this. Do you see how bad this line is? It's actually trash because it doesn't even fit this data. Now at the same time, let's say you instead of linear regression, you do something more complicated and it fits the data like this. Now this is what I call suffering from success. And the reason I call it like this is, see, your testing data will come from outside and there is no guarantee that the testing data will follow a curve like this. For all we know, the testing data is something like this. It's somewhat similar to this, it's somewhat like on a straight line, but it's away. But now you have this huge loss. Or let's say testing data is something like this. Now it's gone. So what you do is, by basically clinging on to your training data in such a way, you overfit or you overshot your whole target. So this kind of thing can definitely happen when you have accuracy as a metric. So when you have accuracy as a metric, this kind of overfitting can happen. So how do you take care of, let's first look at underfitting. So let's say a model is not training only. So how would you do it? If let's say 10 epochs is not, so 10 iterations of changing the parameters is not working, what will you do? You'll increase it, no? 100, try 100 times, 10,000 times. At the same time, let's say your data is not so simple that it can be represented as linear points. Let's say it has to be a curve. So instead of linear regression, you do something else. Now let's say you have your data like this, 0, 10, 100, 10/6. Let's say you have data like this, only 4 points of data. Now if you were to plot this data, how would it look like? 0, 10, 100, 10/6. Do you see how this point can be an issue? Because when you basically learn the data, this point will cause a huge loss function, right? If your curve is like this loss function will be enormous. So these kind of outsider data points are called outliers. Now what you want to do is, you want to detect and remove these kind of outliers. See, how many of you have taken computer science in school when you were small? Like, did you have CS in your, like tiny, you're talking like 3rd grade, 4th grade types? Okay, have you heard of the term GIGO, which was taught then? Garbage in, garbage out. Yeah, this is basically that, okay. So if you give nonsensical data points like this to your model, it's going to learn that. And then it spit on your face only saying, why did you give me this data? So you have to remove such kind of data points, okay. So you have to make a data more streamlined. Now at the same point, not all points are like this. Let's say you have 10 features. One features from 0 to 1 and one features from 0 to 10,000. Now if you have larger values, the model might go biased towards those values. So what you typically do is make all features of the same range or similar range. That way you get a more streamlined model. Okay? So that's how you deal with overfitting. And with overfitting, let's say you learned in such a way that it basically follows your input data. What you do is, you have something called validation testing. So what that means is, in your training data only, after every iteration, you check it with a small sample of it. So let's say you have 100 data points you put for training, out of which you actually train only 90, and you put 10 as some kind of this thing. So let's say, at the event analogy, let's say you're doing an assignment with your friends. Let's say one of your friends has actually completed the assignment. And obviously I do not condone plagiarism for anyone watching, but let's say let's say you're doing an assignment and you're asking a friend to help you out. Your friend says, no, I'm playing what game do you play, PUBG or something. Let's say I'm playing Call of Duty, I don't want to do. He'll say, okay, fine, I'll do first part, you see if it's right or not. So that is validation. So while your model is training only, you see how well it's doing at intermediate points of time by taking validation data. So that's called validation sets. And cross validation basically is like madness, okay. So let's say you have 10 points. You take each set of points. So let's say you have your data is like this. Sorry for doing this. Let's say data is like this. Let's say this is training data. You take a sample of 10 points for your validation. So what you do is, you take every sample like this. You take every sample of 10 points and see at each sample how it's performing. And let's say you have 10 models. You take for all the samples, and at the end you will get a very robust model because you've tried it or not. So this is called cross validation. Okay, is this clear to everybody? Okay,
Cross validation.
okay, yeah, no problem. See, basically what cross validation says is, give me a second. What's your name? What's your name?
Rahul.
So Rahul's doubt is basically about cross validation. Okay. So what we do is basically, let's say you have 100 points in your training set. Okay. You actually update the weights on 90 points and you keep 10 points out for validation types. So now these 10 points, do they necessarily have to be the first 10 points of that 100 set? It could be anything, right? So what you do in this kind of k-fold is, you take 90, 10, then you take 10, 80, 10. So like the first 90 points as plain, last 10 points as test. Then one more module you make, which takes the first 10 points as plain and the remaining as test. Like this. Time to return to this. So let's say you have 3. All possible combinations. So let's say you have 3 things, 3 points, out of which you're taking 1 as test. So first you take this one, then you will take this one, and then you take this one. Okay? So you're taking all possible things. And how many are taking? K is 3, so K4 is 3. Like basically you're dividing your data and you're making a model based on every sample you're validating on. And now once you've done that, you said that I've tried out everything I know. Your friend says I've tried everything. This is what I wrote in my assignment also. That is K4. Okay, is that clear? Do you see why this is better than just choosing it on one particular thing? Let's say if you were to do this, only this. Do you see why doing all 3 combinations is better than just this? Because your data can have multiple ranges. No, it's not like your data is very streamlined. Not like, or let's say your data is imbalanced. There's a very good chance that your one thing that you take contains all of the minority classes. And so your testing accuracy is basically 0. So let's say if you have 90 points of this, out of which 80 can be taken, let's say you're taking 90 points in the kind data, out of which all 80 are A and all 10 are B, then you'll get very disheartened after seeing it, because as far as your model knows, they don't even know that there's a class B. And next thing you know, you give all class Bs. So as an analogy, let's say if someone is testing my PT back knowledge, they give me volleyball, what will I do? It's like that. So this kind of thing you can avoid if you try K4. Okay, but one thing obviously you might think is, K4 is not very efficient, no? Because now it's like analogy, instead of giving me 3 DT backs, they give me some 300. It will obviously take me a lot more time to classify them, but that trade-off you make between processing time and accuracy, or processing time and how good your model is. Okay, so as an ML engineer, you have to take care of this also. Okay. Now there are many ways to check whether overfitting is underfitting and so on. Most of those things correspond with your test metrics, so like accuracy and other things, or reference score as well. As a rule of thumb, from my advice, whatever I know about ML, don't use accuracy, just use reference score. It's always better. That's my theory. Okay. So we learned about some classifiers. We learned about K and K nearest neighbors. We learned about logistic regression. There are also many more, SVM, naive Bayes, so many others. So how would you choose the best classifier for your problem? So let's say you have data set, you split it into training, testing, okay, you did validation also. How would you choose it? You would first take KN and see how it's working, then you would see SVM, then you would say this one, this was getting 0.5 F1 score, 0.4 F1 score, 0.5 is better, take 0.5. That is typically how it does. See, now technically the idea is you would compute all kinds of plots and you look at all these statistical measures, and based on that you will choose the correct model. Not happening. We all know that. We'll just run all the models and we'll choose the best one. But sometimes this might not also work. If you have, let's say, a potato laptop like mine, it may not always work. But that's the most obvious way. Try them out one by one, choose the best one. Do we always have to use one model though? You've taken the effort of making 5 models. Why are you putting 4 of them to waste? If this sounds a lot like your school teachers, I don't know what to say. But let's say, can we do better? So, should we only stick to one model? What if we can combine all the 4 models? Won't that be a better way? Could that be a better way? So, no analogies here. Answer is we can, and that's called ensemble models. So before we look at these slides, I'll give you the most simple ensemble model. In fact, I'll ask you one. Let's say I have 3 models. I have model, what's your name, sir? Siddesh, yours is? Yours also Siddesh. Yours is Ricky, right? Okay, so let's say Siddesh A, Siddesh B, and Ricky have 3 models. Or let's say Siddesh A is telling if it's a TT bat or not. Okay, so Siddesh A and Siddesh B both say it's TT bat, and Ricky says it's not a TT bat. So what would you infer from that? What would you say? It's a TT bat, right? Because what did they say? Now let's say all 3 say it's not a TT bat. What would you infer? That's what bagging is. Bagging is basically like voting. Okay, you take n models, in this case Siddesh A, B, and Ricky. You find out the prediction, so what class it is, and take a majority. Now, does this sound familiar to you? It's exactly what you people did, first time. It's like KNN. So KNN is this is basically like KNN on steroids. Okay, I'm not sure if we get demonetized, but it's like that. Okay. Now this is a very simple model, but do you see where this can go wrong very quickly? So here I'm assuming that all three of you are similar, are the same in terms of your predictive power. All of you know if one is blind. Yeah. No, definitely. So like what I'm saying is, what if one classifier is infinitely better than the other one? Would you trust them both the same? Answer is no. Which is where boosting comes in. So boosting basically takes, there are two ways of boosting. One way is basically take very bad classifiers and make them learn from each other. So let's say classifier B tells you one class they have better accuracy, classifier A tells you 0 class is better. You merge them and make one bigger model, one better model. You keep on doing that until you get very good models. Now this is actually very handy because these are not required to have very complex models. They build up on very simpler models. So I think a good analogy is perhaps like Lego. Let's say all of you have Lego, right? The building blocks thing. So how is a Lego thing made? You take two bricks and you put them together. Hopefully you don't stamp on one, and you keep on making them, right? So that's like boosting basically. Now bagging on the other hand is like voting. Okay, typically. So all of you from different colleges, I assume. So you must all have like council elections and all, right? So how are they like decided? So how many of you are not from IIIT? So please answer. Right. So do all of you like have council or some student body elections or something? Do you have in your college?
Yes.
You have? Okay, fine. If you don't have also, we have India elections. So, so how do you find out? You assume everyone is voting the same way. You take everyone's vote and you add them up, right? So that's what bagging is. Okay. There's also stacking. Stacking is very interesting. So one form of stacking is basically, and this is used in multiple different things. Is let's say you take a classifier A and you feed its outputs to B and it keeps on going. Now certain times this A need not output just the classes. Maybe it can output something else. So basically it's like take my homework and copy it so it doesn't look like mine. And that keeps progressing. Okay, again I don't condone plagiarism. Okay, now we saw so many things to take care of. Now we saw like what if your data is not balanced, what if your data is underfitting, what if your model is underfitting, what if this board is broken. A lot of things we looked at. Let's take a breather. Let's do something fun. So please sit in pairs. So if you're, maybe you can come here. Sudesh, okay. Maybe you can come here because you have to sit in pairs. So two of you should sit in pairs. So if there's someone's not in a pair, please go sit in pairs. Right. So the idea is at least one of you two should have a laptop. That's the idea. That's why you're sitting there. No, it's okay. If anyone has a phone. And the laptop should have a webcam, okay? This time. That's important. I mean, both of you have this kind of person. And I'd encourage one of you to come in. Come in. So mind if you don't know the GDC lead for that college. He's also very encouraged to be computer tech. Come on. So scan this QR code please on your computer and please go to this. So we'll be doing something fun. We'll be making another classifier, but luckily we will not be writing any code. The Google team will do it for you. So this is before the Google team. Stay tuned for that. Okay, I hope the second part is fine in terms of speaking speed. Okay. Sorry, I speak really fast normally. Okay, has everyone scanned the QR code? If you haven't, this is the link. You can copy and paste it. Okay, it will give you some kind of permission to enable webcam. Please say yes. Any issues in opening the link? Anybody? Please raise your hands up. We'll come to you. No? Okay. So I think that yes. Okay, everybody done? Anybody still not done? Please raise your hands up. Okay, good. Oh, you need that? Okay. Anyone is fine. So that's all for anyone else. So what this is basically a classifier. Okay, so if we have class 3, you can press X or something. So what this is basically an image classifier. Like we said, no, human versus dog. In this case, it will be mine versus Vijay. So what we'll do is, so mine you can start. What you stand in front of the camera, please. So mine you have to, and this is for all of you as well. If you get a pop-up, click on allow. You can trust Google, guys. Nice company. So I'll hold the record, and ideally we want like some 20-30 samples. Okay. So mine you can do all kinds of poses, whatever you want. And this is for all of you as well. You can also look at the camera and stuff. Okay. So now I'll start as well. Okay, now after I've taken a few samples, I'll give you some time to take a few samples, please do that. Then you can also rename your class, in this case I'll put okay, take at least 30 samples. Even more is better, but it take longer to ready. Okay, everybody done? Anyone left? Please raise your hand. Okay, after you're done, click on this train model, okay? And if you're taking photos, please continue. But just train after you're done. This will take a few minutes. Can you see the 0 out of 50? This is epochs. So we saw the number of max items. This is max items. So, okay, all of you are done. Anybody done? If you're done, please be wait for 2 minutes and continue. So people at home, you can also try this with your friend at home, or you can self also do one course. Please raise your hand up if you are actually doing this. Or if you are done, please raise your hand up. Okay, okay. Please click on modern trend. If that's also done, then please wait for a minute. Or actually we'll do it now until it's training. So what we'll do is now I'll stand in front of the camera and you can see, I want you to look at this, okay. This is the confidence. Like I said, no probability of how confident it is. This number here, bottom, this is basically the percentage confidence. So right now if I stand, you can see it's quite confident it's me. Now if mine stand, can you see how it's shifting? So this has a pretty good classification accuracy. Okay. If I go change this, and if I go, you see? Now, cool. Fine. Now I encourage all of you to try it out. Maybe put your head in whatever it is that you. Okay. So this product is known as Teachable Machine by Google. And it's a very powerful product. I'll go to my next one. Okay, now just to recap, I'll just do it again with what we used throughout the which is black or red. Now we can see that this is red, this is black. Okay. Now after you've tested it out, I want you to click on this export model. Just click on download menu. Yeah, just click on download my model. This will take some time. Okay, excellent. So this is your souvenir for this session, but the session is not over yet. Now, a good question I might be thinking about is how do they do it? How is this done? What is this crazy thing? I can't answer that in very much detail, but they do use very complex neural networks and they use something known as transfer learning. Now you've downloaded the model, so that is a neural network in some extent. Now one question is, well, where do you learn about this? Come to next session. Okay, next session is about neural networks, and it's what I call big brain time neural networks, if that makes sense. We will release a date for that, but it will be very interesting. Obviously, we will not go into the detail of how teachable machine is implemented, but you will build your own neural network from scratch. If that's interesting, we'll come to the next session. So thank you everybody, and thank you. Thank you. If you'd like to post about